Ever wondered why your air conditioner or heater works? Well, you have to thank convection for that. Convection is the transfer of thermal energy through fluids, and without it, your room would cool down or heat up much slower. But it's not only your room. Convection is found everywhere in nature, from freezing ponds to weather patterns. In this video, you'll learn why convection is so important and how it works. Convection is the transfer of thermal energy through fluids, including water, air, liquid metal, etc., etc. Recall how we learned in physics that thermal energy flows from high temperatures to low temperatures simultaneously? Well, in this case, since the thermal energy isn't fixed in one place like a solid is, it's able to drive movement in the atoms that contain the energy, which create this current of energy flow. Convection is not only related to your room temperature, but also found everywhere in nature. For example, convection currents form because of the temperature difference between hot and cold air, creating weather patterns in Hadley cells. Let's observe the weather patterns of regions near the equator and use convections to explain it. This is a diagram of two Hadley cells, which are circular currents of air in the atmosphere that form because of convection. Between the two Hadley cells is the equator. As we all know, the equator is the hottest place on Earth because it receives the most amount of solar energy from the sun. This causes the air near the Earth's surface and equator to warm up, decrease in density, and making it rise. As the air rises, it simultaneously cools down, which causes the moisture in the air to form droplets of water, creating huge amounts of rain. As the now dry and cold air reaches the top of the Hadley cells, it increases in density and flows downward again, is heated up again by the Earth's surface, and the cycle continues. To calculate the heat transfer rate between two materials through convection, we need to use the Newton's law of cooling, which states the heat transfer rate is directly proportional to a material's temperature and the environment's temperature. The law can be expressed as the equation Q equals HA delta T, where Q is the heat transfer rate, H is the convection heat transfer coefficient, which is given and fixed for each material, A is the exposed surface area, and delta T is the temperature difference between the two materials. This law can be applied to calculate the rate of fluids cooling another material, such as how fast a cup of hot water warms up the mug, how fast a certain type of glass changes temperature when placed outside of skyscrapers that experience high wind speeds, or even how efficient your CPU is with fancy liquid cooling. An important limitation of this law is that it's only suitable for calculating scenarios where the properties of the fluid, such as its velocity, aren't changed too much by the temperature. Let's take a look at an example problem. Today, I'm using an example problem written by the Engineering Toolbox. In this scenario, a fluid flows over a 4 meter by 2 meter plate. The plate's temperature is 50 degrees Celsius, the fluid temperature is 20 degrees Celsius, and the convective heat transfer coefficient between the liquid and the plate's material is 2000 watts per meter squared degrees Celsius. Alright, I've got my notebook and my pen. Let's solve this problem. So we need to first calculate the surface area of the plate, which is 4 meters by 2 meters equals 8 cubic meters. Next, using the Newton's law of cooling, we can calculate that the convective heat transfer between the plate and the fluid is 2000 watts per meter squared degrees Celsius times 8 square meters times the temperature difference, which we can calculate right now, between the fluid and the plate is 50 minus 20 equals 30 degrees Celsius. So that's the temperature difference right here. Okay, now we just need to all multiply this together to get 480,000. And remember, the unit here is watts because the meter squared and degrees Celsius cancel out. And that's how you solve this problem. So what have we learned today? We learned that 1. Convection is the transfer of thermal energy between two fluids. And 2, that convection is found not only in your room, in your air conditioner, or in your heater, but also in many places in the environment. Number 3, we learned how to use Newton's law of cooling to calculate the rate of convection heat transfer between two materials. Thank you for watching. Now, let's take a look at 3, 2, 1. Now, let's take a look at an example problem. Today, I'm using an example problem written by the Engineering Toolbox. That sucked.